Hello. So last time we discussed informal null hypothesis testing, where we were looking at effect size and sample size and determining if this informal way of testing is going to provide us likely information as to whether or not this relationship truly occurs in the population or not. Whereas if we have a large enough sample size, regardless of how large your effect size is, your Cohen's d or your Pearson's r, if you have a large enough sample size, chances are that relationship is really prevalent even in the population in question. So today we're going to be discussing formal null hypothesis testing. So this is where we're actually using statistics. This is where we're actually conducting tests where we have we can determine with certainty using p-values and test statistics, critical values, etc., that, hey, we would reject or we would retain the null hypothesis. So some examples of null hypothesis tests that we use, some inferential statistics that we use. Common one is a t-test. So this is where we're comparing groups based on the distribution of the t, well, based on the t distribution. Every distribution for a t-test has a different number or has a different distribution based on the sample size. So if you have a sample size of 30 for a t-test, that would be different than the distribution for a sample size of even 29 or 31. Again, we're using this to compare two groups. So there are different types of t-tests. We have one sample t-tests, independent sample t-tests, and dependent samples t-tests. But ultimately, the theme for t-tests is that we're comparing one group to another. And we'll get more into detail as to differentiating those as we go on. ANOVA, also known as an analysis of variance. This is where we're looking at the differences in the means for multiple groups. So whereas t-tests, where we're just looking at two groups, with an ANOVA, a one-way ANOVA, we're looking at three or more groups. So very similar to t-tests in the sense that we're still looking at groups. It's just that with ANOVA, there's more than two. Pearson's R is another hypothesis test. That's both a measure of effect size as well, again, Pearson's R 0.1 or negative 0.1 is considered weak, 0.3 or negative 0.3 is considered medium, and 0.5 or negative 0.5 is considered strong. But this is looking at the strength of a linear correlation. So that's just, the line rise over run, essentially. And chi-squared, not chi or chai, but chi-squared, that is when we have categorical variables for both variables are categorical. So we're looking at, men and women and whether or not they purchased a ticket, yes or no. Both of those are categorical variables. And that's just looking at the frequency of responses and seeing if there's any significant difference between maybe men purchased more tickets or maybe women purchased more tickets or whatever. But the ones that we'll be using primarily, especially for our final projects, are likely going to be t-tests and maybe an ANOVA if you have more than two conditions. But let's get into it. So we're going to start by discussing degrees of freedom. Degrees of freedom is used for t-tests as well as ANOVA. And this is just essentially making adjustments for when you don't have access to the entire population, which, as we so often do not, we don't have access to the entire population. For your final projects, you guys are looking into college students or men and women or, whoever it is that you're trying to generalize to. Well, you're taking samples of them. You took 60 college students, or you took 30 men and 30 women, or whatever. Clearly, there's way more than 30 men or 30 women in the world. There's certainly more than 60 college students in the world. So anytime that, most of the time, if not all the time, we're using degrees of freedom when we're going to be using t-tests and ANOVA. It's essentially just accounting for what we don't know. Again, we're taking samples and we're inferring them to the population. even when we have a large sample size, if we have a sample size of 100, 200, 1,000, that's still not the entirety of the population in question, especially if we have college students or just men and women. So we use degrees of freedom for t-tests and ANOVA because those two tests deal strictly with samples. You're taking, 50 men and 50 women in this condition for a t-test, let's say, an independent samples t-test, we have two groups. Maybe you want to look at the difference between history majors, psych majors, and English majors in their GPAs. That's three conditions, three separate conditions, those three different majors, and you're comparing them. You would use an ANOVA. But ultimately, you're still taking samples. And degrees of freedom essentially accommodates for what we don't know. It's accommodating for that missing information of the rest of the population, not just the X amount of people in our samples. So there's different ways to calculate degrees of freedom depending on the test that you use. For one sample t-tests, you calculate the degrees of freedom by taking your sample size, your n, your lowercase n, minus 1. That gives you your degrees of freedom for a one sample t-test. For an independent samples t-test, you take your sample size and subtract 2 for the number of groups that you have. You have 2 groups for an independent samples t-test, maybe comparing men and women, let's just say. To calculate the degrees of freedom, you take the total number of people in your sample. So you got 30 men, 30 women, that would be 60, minus 2, since you have men and women 2 groups. So your degrees of freedom for an independent samples t-test, where you're having 30 and 30 in each group, would be 58, 60 minus 2. And this is just another breakdown of that. So group 1, you take your sample size minus 1. So 30 minus 1, 29. And then another 30 and minus 1, 29. 29 plus 29 is 58. So any way you slice it, you can take the degrees of freedom for individual groups and add them together, or you can just take the total number of people in your sample and subtract 2. And that would also, it gives you the same degrees of freedom either way for an independent samples t-test. So degrees of freedom, that kind of covers that. It's just accommodating. The reason why we use degrees of freedom for samples tests, independent, dependent, ANOVA tests, is because we're looking at samples and we kind of have to use the degrees of freedom as a way to accommodate for, outside of the sample, the rest of the population. So the t-distribution is a type of standardized score. A t-score is, you calculate your test statistic, your t-test statistic for t-tests. T-tests use the t-distribution, the t-statistic, and it makes it pretty easy. T goes with T. And like I said earlier, each sample size is a different distribution. So, when you have a sample size of 29, that's a different distribution than 30, which is a different distribution than 42, etc. But it starts to get normal for a t distribution at approximately a sample size of 30. So that is just that's why we like having larger samples. We start to get normal at about 30, and even more so is even better. So with the t distribution, it's similar to a z distribution in the sense that, we can apply it to, but with a z distribution, it's just one size fits all. There is no different distribution for z for each sample size, unlike t. And it's, again, normal distributions, they're symmetrical. We don't have the true population mean because we're looking with t distributions at sample means only, but that's accommodated for, it's accounted for in a t distribution. It assumes that the population that we're measuring, so the population of all men, the population of all women, in whatever variable we're measuring, self-esteem, stupidity, attractiveness, whatever, we assume that in the population it's distributed normally. And another thing that t distributions tend to assume is that the sample that we have is randomly selected from a population, which we never really have true random sampling. Again, for your projects, you all have convenience sampling. You're posting your surveys on social media and your friends and family are taking them. So that's a convenient sample. So that last assumption for t-tests, where the sample is randomly selected from the population, it's pretty much always violated. It's never actually it's never something that actually happens. But you know, we just kind of tend to sweep it under the rug and say, nah, use the t-test. Use a t-test, it's fine. But that is an assumption for t-tests. So just kind of going into the different types of t-tests. So a one sample t-test is where you have one sample. So typically problems that have a one sample t-test, you'll be provided only one sample size. That's kind of my rule of thumb, or my kind of cheat to know if you're dealing with a one or a two sample test. Just look how many times they mention n equals something. If there's n equals 12, and then another one is n equals 15, seems like there's two samples there. If there's only one mention of sample size, oh, we have a sample with a sample size of 15, and we're comparing it to a population, blah, blah, blah. That's only one sample. Basically, just count the sample sizes and you'll know if you are dealing with a one or an independent samples t-test, at least, you know, just to determine if it's a one or two. So for a one sample t-test, you're taking one sample mean with its sample size and comparing it to a population or a hypothetical mean. So you can compare, you know, 50 college students to see if they eat an average of 2,000 calories a day. That average of 2,000 calories, that doesn't have a sample size. That could be like, oh, the American average is 2,000 calories a day, or the health administration, it requests eating 2,000 calories a day or something. That mean that you're comparing to is just kind of hypothetical. So for the null hypothesis, we're saying that the population of our sample in question, so the population of college students eats the same amount of calories as the average 2,000 suggested calories a day. And then the null hypothesis, that H1 below, is saying that they're not eating the same. They're not eating the 2,000 calories a day. So there's the formula for one sample t-tests. Again, we're not going to really deal much with one sample t-tests, but it's essential to just know that there is more than independent and dependent samples t-tests out there. So looking at an example, we're trying to see how people rate themselves as how friendly they are on a 7-point Likert scale, where 4 is considered that hypothetical average. So we have our hypothetical mean of 4, and then we have our sample size of 40, that n equals 40. The mean for those 40 people in terms of how they rate themselves, their average is a 5 with a standard deviation of 2. So the sentence below is kind of how, if we were to write an APA style report on this one sample t-test, that sentence below is kind of showing how you'd report that in your results section. So the average friendliness score of the sample with a mean of 5, a standard deviation of 2, was significantly greater than the expected happiness score, where that expected mean is equal to 4. A T with our degrees of freedom here in parentheses, that 39, again, 40 minus 1, since we have one sample. And then our T statistic, once we calculated that using that formula, is 3.16, and our p-value is 0.003. So that would be how you could report that if you were dealing with a one sample t-test. But I'm going to move forward to kind of getting more into the other types. But first, there are ways to calculate p-values. You can use a table. You can use a t-distribution function in Excel, or you can use a t-test function in Excel. So for a t-distribution function, you need to know your test statistic, your t statistic, as well as your degrees of freedom. For a t-test, you can select all of the numbers for the first group, all of the numbers for the second group, determine if you have a one or two-tailed test, which I'll discuss, and then that will give you a p-value. You can use the Excel's analysis tool pack, which I know in lab you guys have discussed. You guys have used that. So you can use that to find your p-value. You can use different statistical packages, different statistical programs, SPSS, or R, those are some common ones. But for our class, we're dealing primarily with Excel. You can also use an online stat site like GraphPad, where you can enter in your sample size, your means, and your standard deviations, and that will give you your p value as well as your test statistic, t statistics. So yeah. So I mentioned about those one or two-tailed tests. So a one-tailed test is where you're expecting a difference to go in a particular direction. So for that one sample test of, our example of, college students, do they eat at the same level as, do they eat 2,000 calories a day, which is the average that's, kind of been hypothesized, or just this provided average. If you hypothesize that, I think college students will eat more than 2,000 calories a day or less than 2 calories a day, that would be a one-tailed test. You're kind of picking a direction, more than or less than, and rolling with it. Typically, we deal with two-tailed tests, not one-tailed. A two-tailed test doesn't assume it's going to be higher or lower. It just kind of thinks it's going to be different. I personally, two-tailed tests are better to determine significance when you're not really sure, or if you can be wrong. You can think, college students are going to eat more than 2,000 calories a day, but when you get the data back, maybe they eat significantly less. However, with a one-tailed test, if they eat way less than 2,000 calories a day, maybe they eat, let's go extreme, maybe they eat 100 calories a day. Not likely, but I'm just going for the extreme in the opposite direction. If your one-tailed test is saying, I think they're going to go higher, but the data that we actually collect says it's way lower, it's not going to be significant. It's not going to say there's any significance. We would retain the null hypothesis, because essentially we are only looking in the greater than direction. Doesn't matter how low the calories are actually being consumed. It could be an average of 0 calories or something insane. But if we are thinking it's only going to be higher, essentially we're turning our back to any results that could be happening. Any significant difference, any significantly lower. A one-tailed test is, once we've picked a direction, anything in the other direction, we don't care. It's not significant. So you do have some issues with that. So if you're not entirely sure if, I think it's going to be higher or lower, I don't know, do a two-tailed test. Even if you think, I'm hypothesizing that it's definitely going to be higher, I would still stick with a two-tailed test, because again, researchers' hypotheses can be wrong all the time. You don't decide what happens, the data really tells you. So with a two-tailed test, it provides the openness to, you being incorrect in terms of, I hypothesize it's going to be higher, but it's actually significantly lower. That's fine. A two-tailed test will show you that, accommodate for that. So one-tailed tests are a little funky. So we stick with two-tailed tests. So this distribution is showing a one and a two-tailed test. So these red lines here would be the significance of a two-tailed test. So any of your test statistics that are falling above or below the red lines for a two-tailed test, that's how much you have to work with. It's a little bit less area in each side, so you kind of have to go a little further. But for a one-tailed test, these green lines, it's only one of them. It's not both of them. So if you're hypothesizing as a one-tailed test, it's going to be greater than, it would be from this green line all the way over here, not paying attention to the other side. Again, a one-tailed test is, this is the direction we're sticking in, greater than, and we don't care how low it goes in the other direction. It's only significant if our test statistic falls on this side of the green line for a one-tailed test that's greater than. And the same can be said for a one-tailed test that's less than. We're only looking at this part, only less than this green line, not paying any attention to what's going on greater than. So you have a larger area on one side for significance for a one-tailed test, but it's because it's not being split. So for a two-tailed test, if you have a significance at 0.05, if your alpha is set at 5%, you're splitting 2.5% over here and 2.5% over here for a two-tailed test. Just 2.5% on either side of red line towards the tail. Whereas with a one-tailed test, all 5% is going to be on one side of that green line. So there's a larger part for significance on one side for a one-tailed test. However, that doesn't accommodate anything that's going on the other half. So again, two-tailed, a safer bet to go with, even if you feel like, oh, I'm pretty sure it's going to be greater than, or I'm pretty sure it's going to be less than. Your data can be an error. It could be, there can be just errors in your data. There can be errors in something, or you can just be wrong. You know, maybe the data is changing, and as we, or the trend of that relationship is changing, and, you know, now you got to test for something different. So ultimately, two-tailed tests are a safer way to go. It kind of accommodates for it being greater than or less than, and not just sticking with one horse, which could possibly lose. So dependent samples t-test, we've talked about one sample. So now we're going to talk about dependent samples t-tests. So this is looking, comparing two, you're looking at two groups again, which is what dependent samples does. However, it does it a little differently. These two groups that we have are two paired samples. So it is, these dependent samples tests can be used when you have a within subjects design. Again, as a refresh, within subjects design is that one participant is participating in both conditions of your experiment or of your quasi-experiment. One participant is doing both. Or it could be a pre and post test design, kind of, you can think of it as like a before and after test. So if I were to give you guys a final for research methods on day one of class, and then give you the same final, the final day of class, you know, when I should give a final, I can do a dependent samples t-test to compare the differences between your scores. It's the same lot of you who are taking that test the first time, the pre-test, the before the class, and the post-test after the class. It's the same people who are taking that test both times. So again, that's an example of a within subjects design as well, but it's kind of different. It's referred to as a pre-post test. So, so with a dependent samples t-test, it's kind of done similarly as a one sample test, in the sense of we're not really, the way that we calculate t-tests is done through finding the difference. So we would take your scores the first time you took the test and the second time and subtract them. And that difference between them is what we're using for the analyzed results for our analysis. When we have a null hypothesis, it's saying that the groups are the same. So our null hypothesis for a dependent samples t-test would be that the differences between this is 0. They're the same. So since we're subtracting one group from the other, to have a null hypothesis of saying there's no difference between them equal to 0 is saying that basically they're the same. You know, that 5 minus 5 is 0, 6 minus 6 is 0. When you have groups that are the same, or at least, you know, statistically similar in the sense that we would retain the null hypothesis, it's saying these groups are close enough to where there's not really a significant difference between them. So here's an example of a dependent samples t-test and how you would really report it more so. So if we had, again, a before and after test, a pre and post test, where maybe it's a quiz, a 10-point quiz, right? And the before is, you know, at the start of lecture, maybe I'm going to give you guys a quiz on lecture, on like some content that we're going to learn in lecture. I give you a quiz on that material at the start before we even go over anything, and I give you guys a quiz. Then we do the lecture, and then I give you a quiz after. That could be, you know, something. So we have our before and our after. So to find the difference here, it's just 5 minus 3 is 2, 7 minus 6 is 1, 8 minus 8 is 0, and 3 minus 0 is 3. So that's where we're getting these difference scores, those numbers 2, 1, 0, 3. We're subtracting one group from the other. So this n of equal to 4, that's referring to the number of difference scores we have. Keep in mind that these are all the same people. It's still Bob scored 5 first and then 3 second. Jim scored 7 first and then 6 second. Tammy scored an 8 and then an 8 again. And then, you know, Joe Exotic scored a 3 and then a 0 or whatever. This n equals 4 is related to the number of difference scores we have. And then the mean, we're taking the average of the 4 difference scores, and the standard deviation, we're taking the standard deviation of these 4 different scores. So, excuse me, if we were to analyze this, do a dependent samples t-test, we'd say, oh, results indicate that while depression scores were lower on post-test, so this is a depression inventory. So while depression scores were lower on post-test with a mean of 5.75, excuse me. So here we're taking the average of this as we report it. To do the analysis of a t-test itself, these are not the numbers we use, but as we discuss it in, let's say, an APA-style research report, we can say, oh, the scores were lower on the post-test with a mean of 5.75 and a standard deviation of 2.2, then the pre-test with a mean of 4.25 and a standard deviation of 3.5. This difference was not statistically significant. Degrees of freedom of 3, the test statistic is equal to 2.32 with a p-value of 0.10. So when we report a dependent samples t-test, notice how the means and standard deviations are still of our groups. We do still have 2 groups, that before group and our after group. It's just that for the analysis of it, we're only looking at the difference scores. But again, when we report it in APA style, we still are reporting the means and standard deviations for our before group and for our after group, for our pre-test and for our post-test. So this is a very small sample. Again, difference scores has a number of 4. So based on our informal hypothesis testing, we know that that sample size of 4 is way too small to really say if this is, I mean, it's not significant anyway if alpha was set at 0.05. But even if it was, that sample size is too small for us to go, oh my God, look at this relationship is in the population. You need a bigger sample size. Okay, so for independent samples t-tests, this is used to compare 2 separate samples. So now we're not looking at before and after. We're not looking at the same participants doing, you know, both conditions of our experiment or our quasi-experiment. Now we're more so looking at, you know, 2 separate groups. So this is going to be used for a between subjects design when there's no overlap. There's no, you know, we have 30 in one group and 30 in the other group, and they don't switch over. Those 30 don't switch over to do the other condition. They stick to where they are. They stick to their guns. Between subjects means they're separate. You know, they stick with the one condition, and that's what they stay with. Excuse me. So the null hypothesis is saying that both groups are the same. mu1 is equal to mu2. So the population for one group is equal to the population mean of the other group. So if we're going to do comparing men and women and their self-esteem, let's say, well, that would be an independent samples t-test, assuming the binary of role of sex, where we have men. You don't cross over, again, with strictly binary. You don't really cross over in that. Not assuming, kind of sticking again with binary terms for gender. So as a man, you're not going to also be a woman, and with a woman, you're not going to switch over to the man condition. It's pretty much just as you are. And so that would be independent samples. You're not going to switch over conditions. And with that, you know, we're going to compare self-esteem. So we have 30 and 30, let's say. We have 30 men and 30 women, and we're comparing self-esteem. We don't know. We're not saying, it's a two-tailed test, so we're not going to say men have higher self-esteem or women have higher self-esteem. We're just going to say, they're different. That would be our alternative hypothesis, is that men and women do not have the same levels of self-esteem. Whereas our null hypothesis is saying our men do have the same self-esteem as women. And since these mu1, mu2, that refers to the population. Again, sample t-tests are taking samples and inferring it to the population. So if you're thinking, well, why are we using mu? That's population mean, but you just talked about how t-tests are strictly dealing with samples. keep in mind what samples are doing. They are inferring to a population. So this is saying, our null hypothesis is saying that overall, all men have the same self-esteem as all women. Now we're going to use our sample to figure this out. We're going to use our sample of 30 men and 30 women to, try to figure this out. But overall, what we wish to accomplish from this independent samples t-test is being able to apply this to the entire population. Not just, oh, our 30 men and our 30 women have the same or different levels of self-esteem, but more so women as a whole and men as a whole, the whole population. So that's why our null hypotheses and our alternative hypotheses tend to have that Greek letter mu, which is referring to the population, because we're inferring to that. Anywho, so again, to find the degrees of freedom, well, this is the formula to calculate an independent samples t-test, but for research methods, we're using statistical analysis using Excel or SPSS if you're so inclined. But again, we're mostly focusing with Excel, so you're not going to have to calculate an independent samples t-test by hand. But if you felt the need, there's the formula. And your degrees of freedom is calculated by, again, taking your total sample size. So you have 30 men and 30 women. So you'd have a total sample size of 60 people in your study, and subtract 2, which would be 1 for each group. So that would be 60 minus 2 is 58. So here we go with an example. So again, 60 men have a mean score of 8 with a standard deviation of 4, and 60 women have a mean score of 10 with a standard deviation of 4. So if we were to report this in an APA style report, again, these sentences here are literally ones that you can use, and you can model your reports on when you write your results up for your results and discussion sections that are due on the 24th. You can say, oh, okay, so results indicate, if this is what you have, your descriptive statistics, and you've calculated your independent samples t-tests, this is how you could report it. Results indicate that women scored significantly higher. They have a mean of 10 and a standard deviation of 4. Then men, mean of 8, standard deviation of 4. And here's your test statistics. So you have, or your t-test results. So T, degrees of freedom of 118. Again, keep in mind that it's our total sample size. So 60 plus 60 is 120. Our total sample size minus 2. So that's where we get that 118. That's the degrees of freedom that's in the parentheses. Equals 2.74, which is the number we would get from doing the independent samples t-test formula from the previous slide. Our p-value is less than 0.01 with our Cohen's d of 0.50. This difference constitutes a medium strength relationship by Cohen's guidelines. So if this was your data, if you have 60 men, 60 women, mean score of 8 and 4 for standard deviation for men, mean of 10 and standard deviation of 4 for the 60 women, this is how you could report that. So when you guys are doing your analysis, be sure to look back on this PowerPoint and kind of, if you're having trouble reporting your results in English and not just, T118 equals 2.74. If you're trying to think of how to kind of translate that into how it relates to your study, kind of look back at this and see, oh, okay. So the two groups, results indicate that women scored significantly higher. You shove in the 10 and 4, than men, 8 and 4. And then since you do have statistical significance, that's why the sentence states results indicate that women scored significantly higher, because you rejected the null hypothesis. Your p-value is less than 0.05. It's less than 0.01 for God's sakes. And also make sure you report Cohen's d. And notice that these two sentences also show, discuss how this is a medium strength relationship. So boom. So ANOVA, I mentioned that this is where we're comparing 3 groups. So the null hypothesis states that all the groups are the same. The mean for the first group is equal to the mean for the second group, which is equal to the mean for the third group. The alternative hypothesis, which could be your research hypothesis, is that they're not the same. So mean 1 doesn't equal mean 2, doesn't equal mean 3. Note that for an ANOVA, the null hypothesis, well, the alternative hypothesis for an ANOVA doesn't really say which group is highest or which group is lowest. It's just saying that none of them are really equal. So if you were to find statistical significance for ANOVA, you don't really know for sure which group is higher or which group is lower. It just essentially says it's different. That's all ANOVA is telling you, which is fine for an independent samples t-test or a dependent samples t-test because it's just two groups we're comparing. So it's like, oh, okay, I know which groups are different. It's just these two groups. But for an ANOVA, we don't have that information. So for an ANOVA, we kind of have to go a step further if we have statistical significance, if we reject the null hypothesis. So one thing to note about ANOVA is that it does not use the t statistic. That t statistics are used for t-tests, but with ANOVA, it uses the f statistic, as in why the f is it not just called the a statistic. But the ANOVA test uses the f statistic, and we can compare it to the critical f value, or we can find the p-value and still find it and still compare that p-value to alpha at, typically 0.05 to determine if we would reject the null or retain the null. But this is where we're comparing three different groups. So with a one-way ANOVA, which is more so what I'm going to focus on in this discussion, is that, again, it tests the differences between, again, at least three groups and see if they differ in any way. It's, again, similar to a t-test, except now we're just tacking on another group. We use a one-way ANOVA when there's only one independent variable. So maybe we're only looking at college majors, and our groups are art majors, history majors, and psychology majors. Three groups, the only independent variable we're looking at is just college major. Again, you can use ANOVA. It doesn't have to only be three groups. It can be more than three. It can be 4, 5, 6. But typically I say three because three or more at least. And so we're going to be looking at the average difference across these three or more groups. So maybe we're looking at the, the stress levels or the happiness levels between history majors, psych majors, and art majors. We're going to measure their stress, give them maybe some sort of stress inventory, and compare the art, the history, and the psych majors, and to see, who has more or who has less. Well, if we were to reject the null hypothesis, that's not saying, art majors are more stressed than history majors, or, psych majors have more stress than art majors. Rejecting the null hypothesis straight off with just an ANOVA, one-way ANOVA, just says they're not the same. And it requires an additional step to determine which one is higher or lower. But there are degrees of freedom comes up again with ANOVA, as it did with t-tests, except with an ANOVA, well, we have more than one group, or we have more than two groups now. So it kind of has to go a little differently. So with degrees of freedom for ANOVA, we actually have two different sets. We have a between groups estimate and we have a within groups estimate. So we calculate the between groups by taking the total number of groups we have and subtracting 1. So K here represents the number of groups. So again, let's stick with that college major question. We have, art, history, and psychology. Our K, the number of groups we have, is 3. So our between group degrees of freedom would be K, 3, minus 1. So our between groups degrees of freedom for that ANOVA would just be 2. Within groups is where the within groups degrees of freedom for ANOVA is where we take the total sample size and subtract the number of groups. So let's say that we still have that same problem of art majors, history majors, and psychology majors. Okay, so we have K equals 3, but to do the within groups estimate, we need to also have the total number of people in our study. So let's say there's 30 in each group. There's 30 art majors, 30 history majors, and 30 psych majors. So add them all together to get our total sample size, 30 plus 30 plus 30 equals 90. And now we subtract the number of groups, which is 3. So our within groups degrees of freedom would be 87, that total sample size of 90 minus the number of groups, which was 3. So 90 minus 3 is 87. So here is just an example. So maybe we're taking, maybe a professor has 3 different sections of a class. Maybe they have a stats class and they have, 3 different sections, and they're taking the quiz scores on the first quiz for their first class, their second class, and their third class. Again, these are between subjects groups, so no person is going to be in the same group twice because each of these groups represents a different class, and this class is all the same. So if it's Psych 42, if it's a stats class, you're probably not going to be enrolled in a stats class in a semester and also be enrolled in another stats class in the same semester, especially if it's, in the same breadth. So you can't be in Psych 42 twice in the same semester. You're taking it once and you're only in that class. So these groups are mutually exclusive. So for those that are in class 1, they're not also in class 2, and they're not also in class 3. They're all between. But again, these are the first quiz scores, the first quiz of the semester. This is what each student in the class scored on them. So class 1, 10, 8, 9, etc. Class 2, class 3. Okay, so there's our 3 groups. And now we want to see the differences between them. So here is a readout of ANOVA. This was done through Excel. And this is what it looks like when you do an Excel ANOVA. So you have a summary of class 1, class 2, class 3. The count here just refers to how many people were in class 1, how many people were in class 2, and how many were in class 3. So that count here is your N, your sample size for class 1, class 2, class 3. The sum is just adding up all the numbers, but it's more so the average that we're looking at. So the average quiz score for class 1 was 8.4, 8.1 for class 2, and 8.7 for class 3. Variance, if we were to square root that would provide us the standard deviation of each of the respective classes. But down here is where we're looking at, this is where we're going to determine the significance here. So this degrees of freedom here, we have the between groups and the within groups. Now keep in mind that for the between groups, that is the to calculate this degrees of freedom, that's taking the number of groups we have, which was 3, and subtracting 1. And then for within groups, it's taking the total number of people, so 10 plus 10 plus 10, 30, and subtracting the number of groups we have, so 30 minus 1, 2, 3, that gives us 27. So I'm going to focus more so on the F, the P, and the F critical. So our P value, first off, is 0.55 if we were to round it to 2 decimal places. So we know off the bat, if our alpha, if our significance was set at, let's say, 5% at 0.05, then with this, we would retain the null hypothesis. This P value is greater than our alpha. But we can also determine significance by looking at the F statistic. So our F statistic here from this problem is about 0.62. And the critical value for F, if our F statistic were to be greater than this, that would be significant. So that's kind of our threshold when we're looking at the F statistic. This F critical here would be our bar that is set for significance. That's kind of like our alpha level if we were to use the F statistic to calculate significance as opposed to just the P value. So 0.62 is not greater than 3.35. So both of these ways, both the F statistic and the P value are telling us to retain the null hypothesis. Our P value is greater than alpha at 0.05, so retain. And our F statistic that's calculated is less than the critical F statistic. So that would also indicate that we were to retain the null hypothesis. So what this is saying for this particular example is that all the groups, all the classes scored pretty much the same across the board on this first quiz of the semester. If we were to reject the null hypothesis, Again, that's just saying that the groups are different. It's not saying, oh, class 1 scored higher than class 3. It's not saying, oh, art students are more stressed than psych students. When we reject the null hypothesis for an ANOVA test, that's just saying they're different. Someone has more or someone has less, but we don't know which. That's where, if you reject the null hypothesis for an ANOVA, you have to conduct a post hoc test to determine which of these means are different, which one is statistically higher or statistically lower than everything else. So this is like a series of modified t-tests. They can be done automatically through online calculators or SPSS. There are 3 typically used post hoc tests. There's Tukey's, there's Bonferroni, and there's Holmes. So these are the most consistently used, consistently supported. So I'm not going to ask you guys to calculate post hoc tests by hand. Again, if you are using ANOVA for your final projects, you would just use the function in Excel or the function in SPSS, but Excel, and just add that Tukey's post hoc to it. So that is our discussion on formal null hypothesis testing. I've gone over the common inferential statistics that you'll use for your final projects. Again, most of you probably going to use either independent or dependent samples t-tests, and there might be a couple of you that are using ANOVA, but for the most part, it's going to be dealing with t-tests.